Great. Hey, everyone. Really good to meet you all. It's a pleasure to be teaching this boot camp. I'm going to be with you for the first 4 weeks. All right, so I'm going to start off taking a little bit of a step back and look at decentralized systems. And the reason for this is that although we're used to working within this space within Web3, it can be easy to forget why we are doing that. Why do we work with blockchains rather than some other architecture and just use a database or something like that? Why have we moved from Web2 to Web3? And I think it's important that we keep this in mind and keep in mind these extra features and these important aspects of Web3 that we get because we're building our applications on a blockchain rather than some client server architecture or whatever. And there have been many problems with centralized systems, and particularly we see these in the monetary systems. We saw banks closing. This is something that continues to happen. Often if they have insufficient capital to keep the bank going. There have been various debt crises over the years, banks closing, and the people do actually lose their savings, even though sometimes there are insurance schemes. Sometimes they fail themselves. They may not work properly. And this has led to an increase of use in cryptocurrencies in various countries because people have lost faith in traditional financial systems. Something that always catches me out with traditional finance is the availability of banks. I'm quite used to the idea that I can interact sort of 24/7 with blockchain, and then when I go to my bank and find it closed, it really does bring me up short, and I have to remember that that's what it really used to be like. But with blockchain, we don't have that. We get they're fully available. The next point, the idea about money supply and the control of a central authority, very much the case. The way that your currency is going to work is dependent upon probably a government who are deciding on monetary policy. And that could mean that there is inflation involved. But you may not know how decisions are going to be made regarding that policy. And those decisions may change over time. With blockchains, that's not the case. You know what's happening. You can see the protocol. You know how the currency works. It's very transparent. And of course, if you're working within a traditional monetary system, and you have merchant accounts, they can get shut down for no reason. People can deny you access to financial services. And this really brings in where I first heard about blockchains was when WikiLeaks was looking for funding, and they had that stopped, and they had to then turn to the blockchain to Bitcoin, as it was really the only alternative then for funding. So there's a great difference between centralized systems and decentralized systems. One of the areas you see this is around access control. And with banking systems, you get layers of access control built in to prevent people interacting with those systems, to prevent fraudulent transactions, etc. So they try to close down the network to prevent misbehavior, I suppose. It's very different with open blockchains such as Bitcoin and Ethereum. So with those, anybody can interact, but there are incentives built into these systems to ensure that those interactions are done correctly and that they promote the behavior that the people who built these systems want to see. So what do we get from decentralization? Well, participation, of course, so these are much more open. This means there's a much wider diversity of people being involved in these systems. One aspect of the way that they work is we need some way of, what I've said here is conflict resolution. We need a way that we can decide if there is disagreement. We need a way that the blockchain as a whole can move forward and decide on different views. Blockchains have the potential to be very flexible. And perhaps the most important thing for me is this idea that we are moving power, we are moving control to the edge, to the user. So when you are interacting with a blockchain, you have control over your assets and you have control over your data. Okay. I'll just quickly go through some basics about the components that make up our blockchain. So they exist upon a network that is built upon the internet. The earlier blockchains used this thing called a gossip network, where the nodes within the system would gossip around information. They would send transactions to each other and data to each other. As we'll see with Solana, there have been improvements on this. But the original idea was this idea of gossiping the network data around. The most important aspect of a blockchain, I suppose, is this idea of a shared public ledger. So this is the idea that you can create a ledger, a list of transactions that have occurred within the blockchain. And this is public, and this is shared to the extent that everybody can do this. Now, it's easy to think of this as being some kind of central database or something like that. That's not the case. These are ledgers, these are local sets of transactions that are maintained by the participants within the system. The final important aspect that was needed for blockchains is cryptography. And this is because we are working in a hostile environment. And we may have difficulty otherwise. If we didn't have cryptography, we may have difficulty being confident that the transactions were not being interfered with or changed. And so we need quite a bit of cryptography to help us and to help us secure the network and to give us confidence in the way that the system works. So those are some components. They give us various properties and features of a blockchain, such as transparency and the fact that the state of the blockchain is verifiable by anybody within the system. And we have this concept of consensus, the idea that even if we have potentially different views of the system, of the state of the system, we can come to agreement about that. There is some kind of mechanism that will allow us to come to agreement and allow us to move forward with our blockchain. The fact that we have cryptography and the nature of the network gives us resilience and also censorship resistance. I'll come back to that later because that was very much an ideal in the early days, the idea of the censorship resistance. There are ways that people do try to censor transactions on blockchains. So it's not a straightforward concept, and but I'll talk about that in a later lesson. And then the final point here is the idea of interactions being tamper-proof. So if I create a transaction and send that into a blockchain network, I am confident that that transaction is not going to be corrupted in any way, that it is going to be received by the participants in the network exactly as I sent it. So, yeah, a little bit more detail. The network itself is a peer-to-peer network. So this means there's no central authority. People can join and leave the network at any time. The network as a whole will still be maintained. The messages going around the network are transactions. These represent changes of state within the network. We have a set of rules. The protocol itself is formed of rules that say what a transaction can look like, what makes a valid state transition within our network. A good way to think about the blockchain itself is to think of it as a state machine, which moves from one state to another according to the rules of consensus. We usually look at the blockchain in terms of blocks, and there's cryptography around these blocks that make them secure, and these form the basis of our ledger. I'll talk about the consensus algorithms in a moment. But this is the means by which we come to agreement about the changes that are happening within the system. And I mentioned earlier the idea of incentives and behavior within a system. And this is down to sort of game theory and incentivization schemes that are there to secure the state of the system in this open environment. And this is usually done by economic means. We make it economically, we make it profitable for people to behave in a certain way and to follow the rules, and that's the incentives. And then all of this needs implementing. So we have what are perhaps confusingly called clients. So this is the client software that runs on the nodes that actually implement our network and implement the blockchain as a whole. I said it's useful to think of it as a state machine. So here's a little diagram to show you what that looks like. So we start off in one state. We get a block of transactions coming in. We apply those transactions to the state, and that gives us a new state. And so that just keeps going. And yeah, you definitely want your blockchain to keep going. You don't want it to get stuck at any point. The structure of the blocks, obviously this is going to be different for different chains. This gives you an idea of what Bitcoin kind of looks like. It starts off with a block called the Genesis block, and then we have blocks being produced there. They contain transactions, and they have a header, which is metadata. It will have timestamps, etc. But it also has a link to the previous block, and these links are cryptographically secured, so that you can follow these links back and see how the blocks are related to each other. Here's some of the data in the first Bitcoin block, and you can see if you look at the ASCII characters there that there's a little data area available in each block. You can put just arbitrary data in, and in this one they put the headline from the Times newspaper at that time, and it was appropriate because it's talking about the financial crisis of 2008, 2009, which really did give rise to the use of cryptocurrencies and provided some of the desire for that. Okay. How have the prices performed among some of the big blockchains since then? Well, Solana has done very well, as you can see. This is yeah, a little bit old now, almost a year old, but yeah, certainly it has held up very well. But they've all increased, yeah, generally. And I'm going to look at the different consensus mechanisms associated with these different chains. I don't think, though, you can really draw any conclusions about the price increases and the consensus mechanisms directly. It's much more complex than that. Okay, let's turn to some cryptography then. So one of the fundamentals, fundamental building blocks of cryptography that's used within blockchains are elliptic curves. These are curves that have this kind of equation here, something like this, but with other coefficients as well. Important to note that these will not be, or the way these are used, they're used for signatures, for example. These are not going to be secure if quantum computers come about to become feasible. So it could be that there will be a change. There are some other ways, there are other mechanisms that we can use to do post-quantum cryptography. So we may see those happening in the future. But at the moment, people are pretty much okay with these. We don't think these can be broken at present. So these are quite widely used. And elliptic curves are quite efficient. For the same key size within an elliptic curve, you get more security than you tend to get for other types of cryptography. Yeah, such as RSA. So what do I mean by a key and an address? Well, a big breakthrough that happened in the 70s was the idea of asymmetric cryptography. And this introduced the idea of having two keys, a private key and a public key. And if you've used a wallet, you should have hopefully got this idea. The idea that the private key is the thing that you use to control your funds, and it has to be kept private. If you leak that information, then somebody else will control your funds. In terms of the cryptography, the process we have is that this private key can be created, and really it's just created at random, but it is such a large number that we can do this without worrying about there being collisions. And from that private key, we can derive a public key, but these are associated with each other. They have a relationship to each other. And then from the public key, this gives you an address on the blockchain. There's maybe some derivation done to give you an address on the blockchain. Okay. All right. So that was a little bit of background for you about cryptography and decentralized systems, etc. Let's move on now to dig into Solana more specifically. So we have the concept of blocks in blockchains. So yeah, we have blocks in Solana as well. But I do see this concept changing over time. I think certainly with Bitcoin, the first blockchain, it was very much, it was a good idea to have a block as a kind of a basic unit. But when you think about what's happening within the blockchain, within the system, really what we're doing is we're using transactions as a way of changing the state of the system. And then these are put together into blocks to make that unit. But over time, we do see some change in emphasis, I think, so that we, yes, blocks are still important, but we also see transactions as being seen as important as well. And we see the ways of viewing the changes of state, looking more at transactions as well. But anyway, we still have blocks. They're produced, but in Solana they're produced very quickly, as you can see there. The network itself is very different, really, I think, to the original types of blockchain networks we had. So we talk about a cluster, which is a set of validators, a set of people running client software. And these work together to provide services to the people who are providing transactions. So people want their transactions to be included and processed in the network, and the validators are there to provide that service. So they can work together to provide a cluster, but there could be many clusters. The cluster itself will have a genesis block. This is really the configuration of it. Now, if the clusters have the same genesis block, they can work together. They really are effectively the same cluster. Otherwise, they are different clusters. They won't be able to interact. Okay. Now, a tool that I think is perhaps undervalued by developers is the block explorer. So early block explorers, they showed you blocks, they allowed you to drill down and look at details of transactions, and that may have been it. But over time, they've become much more sophisticated, and they allow you to look at metadata about the system, the number of transactions that are going through, the price of the native currency, etc. And all of these things have been added, and particularly with blockchains that allow smart contracts or allow programs, they're very useful. They allow you to drill down and look at those contracts or programs, but they also may allow you to interact with them. So they do form a very rudimentary kind of client that allows you to interact with programs as well. And so they have become much more sophisticated and much more fully featured over time. I've just got some examples for you there. You can see other types of things. Also provide information about the networks and the validators that are there, and the throughput of the network as well. Okay, so let's talk about mempool and the transaction life cycle. So when we try to interact with a blockchain, we send in a transaction, and this transaction is destined, hopefully, to get put into a block and become part of the history of that chain, part of the canonical chain, and is going to affect the state of the system. But before that can happen, it will be in a pending state. So it has arrived in the network, but it hasn't actually made a state change. It hasn't been accepted. Now, again, in different types of blockchains, in different networks, these things are handled differently. And we'll see again how Solana does this perhaps in a better way than some of the earlier systems. But in some of the earlier systems, these transactions would just be there pending, and they are regarded as being in what is called the mempool. Now, this isn't a centralized sort of repository of transactions. These transactions will come to a particular node within the system, and then the node will be able to pass these on. So the transactions do become available generally throughout the system. And it's that really that is seen as the mempool. But one of the reasons that this is important is that the demand for inclusion within the blocks often outstrips the supply. So we have more transactions looking to be included within blocks than we have space within the blocks. And so transactions may be waiting for a while before they are included. And so this means we'll have a larger mempool. And this is what this diagram is meant to show, the idea that this can fluctuate quite a lot, but at times there will be a lot of demand for inclusion within a block. Sometimes this is also called network congestion as well. And it's interesting to think about how different chains mediate this. So from the point of view of the user, that's the demand side. They are demanding that their transaction is included within a block. And then the supply side is provided by validators who are providing the space in the block, and they are executing those transactions. And obviously, this is kind of a dynamic equilibrium that is going on between these two sides. And different chains have handled this differently to try to get this to work. So it could be that you will increase the fees that users are charged as the blockchain has increased demand. So you'll increase the fees to try to reduce the demand at that particular time, and therefore allow more transactions to be processed. But we'll look at what Solana does in a moment. But as I say, this is a dynamic equilibrium that goes on, and it is something that is quite fundamental. And I think it's important to be thinking about with Solana, because Solana does very much focus on the idea of throughput. So this is a problem that it really does need to solve. Now, I said earlier we had the idea of a gossip protocol in early blockchains. Those are not necessarily the best way to allow information to go through a network. And although it did work with Bitcoin and with Ethereum, and it means that transactions do get passed around the system and do get distributed everywhere. The problem is that it's not very focused, it's not very efficient. So one of the innovations that Solana had was to try to make this more efficient, and particularly to think about where this transaction needs to go. So you send a transaction into the blockchain, into the system, and you want that transaction to be picked up and put in a block. Well, where does that happen? Well, again, different blockchains, different ways it happens, but you often have this concept of a leader. So there will be somebody, some validator within the system who is going to take that transaction and put it in the block. And the system as a whole has agreed or will agree that that person, that validator, is going to be allowed to have this role and to be allowed to put this transaction into a block. And so the idea that Solana had early on, and this what gave rise to this technology called Gulfstream, is the idea that if transactions are coming into the network, well, we don't want to just flood the network and send these transactions everywhere. That's rather wasteful. What would be better is if we sent these transactions directly to the person who is going to put them in the block, because that's the person who needs those transactions. And that's, from the transaction point of view, that's the person they want to be sent to. And so that's what we get with Solana. The transactions are targeted and sent to what is called the leader. And now this person, this validator, is not the same person every block. It is something that rotates. There's a mechanism to rotate it through different validators. But that mechanism is known. So we know ahead of time who will be a validator at a particular, sorry, who will be a leader at a particular time. And so therefore, we can make a more intelligent sort of targeting of our transactions and send them to the leader when the leader needs those transactions, rather than just distributing them everywhere. Excuse me. And then, of course, having done that, then the leader needs, having created a block, then the leader then pass that back, pass that block back to validators to allow the validators to be updating their own local ledger and their own version of the chain. Okay. And these ideas are very fundamental to the way that we get increased throughput within blockchains. As I said, this idea of an equilibrium happening does rely upon all of this working properly. And if we want to increase the throughput, we want this whole process to be as efficient and quickly as possible. Another thing that we're going to come on to later as well is the idea of transactions becoming expired or duplicated. So we need to think about, what do you do if I send in a transaction and then I send it in again, maybe by mistake. What should we do about that? Should we say, well, that's the same transaction, or should we update the transaction? Is it an update to the previous one? So we have to think about those types of ideas as well. So we have to have some mechanism that allows us to identify the transactions within the system. But also, it would be a good idea to have the concept of a transaction becoming stale, because imagine you're doing some DeFi trade. You're doing something in a DeFi project. You see some opportunity, you get your transaction in very quickly, you want to take advantage of it, but you know that only makes sense within the next few seconds. So you don't want, if your transaction doesn't get picked up for whatever reason, doesn't get processed, it doesn't make sense for that transaction to just to be hanging around for minutes or hours, by which time the prices in the DeFi project will have changed and will no longer be relevant. So for that reason, we also want the possibility to say that transactions have a limited lifetime and they're going to get dropped when they are no longer valid. And again, this helps with the efficiency of the system and helps with throughput, because it gets rid of stale data within the system. Now, something I'm going to also talk about in a moment is the idea of finality. We have concepts of throughput of transactions getting into the system and being accepted and becoming part of the ledger. But there is a concept of, when does the transaction itself become final? So it may start off pending before it gets picked up, and then it will perhaps hopefully get put into a block, and this block will get passed around, and there will be some consensus mechanism that is going to accept this block as being the latest block within the system. And this applies to all blockchains, not just Solana here. we also then have this idea that at what point can we say that that transaction has truly been accepted by the system and is final within the system? And this is a problem for systems such as Bitcoin, because that finality, the fact that you can have confidence that that transaction is now part of the canonical system is not going to change. The time for that to happen can be quite large, and in fact, with Bitcoin, it's more eventual because the possibility of that transaction being changed or there being a reorganization within the chain does go down over time, but it never goes to zero, that possibility. Later blockchains have tried to change this and tried to say, well, actually, for practical reasons, we want to be able to say that a transaction is final. And we want that to be fairly quick as well. We want that to be within seconds, so that if you are doing some commerce, if you want to go and buy a coffee pay for it on a blockchain, you don't want the vendor to be waiting there for 30 minutes, waiting for your transaction to be final. You want them to know that it is accepted, it's not going to change within a couple of seconds. Okay, so that's finality. So throughput. One of the, as you'll see, the driving forces behind Solana and behind the innovations that gave rise to Solana were around scalability. Scalability is a big problem for blockchains. It always has been a real focus for blockchains. People have always been trying to improve the scalability, improve the throughput of blockchains. And one aspect of this, one approach to this is around concurrency. So if you look at Bitcoin, if you look at Ethereum, the way they work is that they have a sequence of transactions coming in. They are processed in order. They make a change to the state of the system, and then the next transaction is processed, and that makes its own change, etc. So they're done one by one. Now, that is a simple way to do things. It's a way that allows us to understand what's happening. It's a less complex way of doing things. But it would be nice if we could speed things up a bit by, for example, trying to process transactions in parallel. Of course, the problem, and this is a general problem in computer science, if you try to do some execution in parallel, but those two transactions are going to interact or update some shared state, then how do you decide how that is going to be done? How can you do that safely? So Solana, I think, was one of the first chains to really address this, and the fact that they managed to work out a way of doing this, I think, is one of the most important factors in their success and their success of getting better scalability. We have seen this being adopted in other chains as well. More recently, we are seeing this increasingly adopted and people trying to do this with other EVM chains. But it is not a simple thing to do. But the problem is, as I say, the idea of how can we safely change or update state that, say, two transactions are both trying to update at the same time. And this is a problem you've probably seen in other areas. If you want to improve performance in a system, you could add more threads to it and do more in parallel. But then you get concurrency problems, and it could indeed slow things down because you have to put effort and processing into handling that concurrency. So sometimes it's better to keep things single-threaded. But it seems with blockchains, and certainly I'll say I think the evidence from Solana would be that being able to do things in parallel has certainly been beneficial. So let's take an example here. Say we have 4 transactions. They are going to update some state. So we've got 3 accounts here, A, B, and C. These 4 transactions want to update these accounts. Now, what Solana is able to do is to look at these and be intelligent about this and make a decision to say, well, two transactions, transactions 1 and 3, both want to update, excuse me, account A. So this means that transactions 2 and 4 we can run in parallel because they're not trying to update the same account, so we can just run those in parallel. The only problem is that we have is with transactions 1 and 3. So immediately then we get the possibility that we could do 3 of these transactions in parallel, and then one of the transactions has to be done sequentially from that. But immediately we get the possibility of greater throughput because we can make a decision, because we have the information available to us to know what state is going to be changed. All right, let's talk about consensus. So we've got a huge network. We've got all these people all around the world who are maintaining this network. They are validators. They have their own state held locally, which they want to reflect the latest state in the system. But how can they come to agreement about that? Particularly if some validators will have seen some transactions, some validators will have seen other transactions. How can we come to agreement about that? And this is particularly a problem in digital systems. And one of the reasons I think that digital systems didn't take off for quite a while was because of the double spend problem, where if you have some digital asset, you want to know if Alice spends her digital token by sending it to Bob, she shouldn't be able to then send the same token to Charlie. So we want the idea that there's only one copy, I suppose, of this digital token. But how can we enforce that without some kind of centralized system? And the way that we can do that is for the participants within the system to come to agreement about the state and to be able to say, we know that Alice sent that token to Bob, so we know that she can't send that also to Charlie. So if we see a transaction going to Charlie, then we're going to reject that. And everybody in the system can come to agreement about that. But how do we actually do that? Well, this is a problem that's been around before blockchain to do with decentralized systems or distributed systems, sorry, in general. One piece of terminology you may see is Byzantine fault tolerance. And this is the idea that a system will have some tolerance. So even if some components in the system fail and there is incomplete information, or maybe even malicious information being put into the system, that the system as a whole will be able to proceed. And there are theoretical limits about how much failure can be involved or how many errors can be in the system. And yet the system can still proceed securely. Okay. Oh, there's the double spend problem. So we have mechanisms, and I'm going to go through those in a second. But something else that I want to bring up as well is another innovation that Solana had, and this is to do with synchronization and agreeing upon sequences in distributed systems. And this is really quite a problem. If you look at Bitcoin and Ethereum, there's no central clock there. There's no real way that you can say that one thing happened before another in a general sense there. The only way that we can do that is to get someone, get a leader, get a block producer to say, well, I'm going to choose this as being the sequence of transactions that are going to go into a block, for example. What Solana was able to do was to provide a kind of a clock, which was done by this thing called proof of history. And this allows different participants within the system to come to agreement about the sequence of events within the system and to be able to do that securely. Other people have tried as well. So Hedera, another blockchain, tried that, relying upon timestamps. Of course, the problem with that type of thing, if you have timestamps, is of course that people could maliciously change the timestamps, or there could just be accidental differences in timestamps because different machines may be slightly out of sync or whatever. So, but with proof of history, we actually get a more of a cryptographic approach and a way to show that things happened in a certain event, in a certain sequence. Now, talking about consensus mechanisms, this terminology is often a little misused. The process as a whole has two parts. The first part is what I'm going to call Sybil resistance, and then the second part is, strictly speaking, the consensus mechanism, although people often talk of them both together or conflate the two. So the first part, this is the things that we get that get called proof of something. So like proof of work, proof of stake, etc., etc. I'll just advertise my own involvement here. We did one called proof of kernel work along with other people. If you get a chance to play around with these things, they are quite fun to try to invent and try to work on something like this. But anyway, these ones are all about finding someone, finding a leader or a block producer amongst the set of validators that we have within our system, and doing that in a way that is seen as fair. So, for example, if you think about Bitcoin, we know that there are block producers producing blocks every 10 minutes. It would, if the same person produced the block consistently for a few days at a time, that would be seen as suspicious. You don't want the same person to be doing that. You want this to be seen as being fair and different people being involved. But then that's not an easy thing to do necessarily in a distributed system. But there are mechanisms to do that, such as proof of work, etc. So that's a Sybil mechanism. That's how we can narrow down our entire set of validators within the system to find one who will then have a special role. The role is going to be producing a block. So they may be called a block producer, they may be called a leader. They have different terminology, but it's the same type of idea. It's a way to pick someone out of the mass of validators as a whole. This is useful because generally in blockchains, you could think that this person is then going to be responsible for deciding the state of the system. If we have the network and within the network, there are different transactions. So here we've got the gray transactions and we've got the green transactions. Some nodes within the network have one view of the state of the system. Some have another view. What we really need is something to give us consistency. So what we do, and here I'm really thinking about Bitcoin, is to pick one of these people at random and say, okay, you choose what the state of the system is at this particular time. And then you show what that is by producing a block. And we will all accept that that block is the state of the system. That's going to be the canonical representation of the state of the system at that particular time. And it doesn't really matter who it is, just as long as we get someone to do that. And as I say, we want that to be done fairly and to be seen to be fair as well. And we have the similar thing in Solana. We want the leader to be there to produce the block, to set up the transactions that are going to be within the block, and then that can be transmitted to the other validators. And an important aspect of that is that the block producer decides the order of the transactions within that block. And that is potentially a very powerful thing, gives them a lot of power. It means that people who are sending transactions will be incentivized to pay the block producer to get their transactions ahead of other people's transactions. There may be economic benefits to doing that. Okay. So as I say, we want the idea of choosing the leader to be fair and difficult to abuse. So proof of work uses a kind of a lottery race to do that. proof of stake uses different methods. Often we have some cryptographic function that is there to give a time slot to validators. And then within that time slot, that validator will be the leader or the block producer. But that's chosen in a random way. But because it's a verifiable random function, we know that has been chosen, randomly chosen fairly. But other things to think about when we're doing this is around a concept called liveness. So we definitely want our blockchain to proceed over time, and we don't have a central authority. So if our blockchain stops, we've got a real problem. So our blockchain must be able to sustain itself, to keep producing blocks over time. And this is the concept of liveness, the idea that the blockchain is live and we'll be able to continue. But what do we do if we're creating slots or something, or whatever mechanism we use? What happens if no block producer is chosen at a particular time? Or if there is one that is there in the slot and should be producing blocks, but doesn't do so? What do we do? And that's all part of the consensus mechanism that we need to be able to cope with this problem. And a point that shows how proof of history and how shows the importance of the idea of time that Solana has a better grasp of, I think, than other blockchains, is the fact that if we need to make this decision, so we need to say, well, this validator should have produced a block by now, but they haven't done so. So we need to move our system on into a different state. We need to say, we've got to move on, that they're not going to produce a block. We need to ask somebody else to do it. Well, how do we decide about that? How can we decide upon a timeout and decide that the time that someone has passed, and do that in a way that is going to be agreed by everyone? And with something like Bitcoin, you kind of don't get that, because with Bitcoin, everybody is just doing everything as fast as they can. But because the lottery takes so long to solve the puzzle, then it's only, on average every 10 minutes that a new one happens. But we know that the effort is continuing, that somebody else will be trying to do this. But with Solana, we have this advantage that if we can get some kind of fine-grained timing available to us, then we can quite quickly say, well, that slot has definitely finished. That validator didn't produce a block for whatever reason. We've got to move on and get the next validator to step up and do the block. So that's how having a reliable source of time can help solve with timeout issues. So that's the first part. That's the Sybil resistance part. That's the proof of ... Once we've got that, and once the person has been chosen, they're going to create a block that needs to be accepted by the system as being the latest block within the system. And we need to come to agreement about that. And oddly, there are very few ways of doing that, really. There are really only three ways to do that. One of them is the Byzantine fault-tolerant way, and there are many different implementations of that. Excuse me. And as you'll see, this concept, this mechanism, was invented before Bitcoin. But then, Bitcoin came about, and we got Nakamoto consensus. So that was another way of doing that. And Nakamoto consensus says that the way that if we have to make a choice between two blocks that have been produced, we have a heuristic to do that. There's a rule of thumb that we can apply to be able to choose between these two blocks, which is effectively to say, it looks at the difficulty that was, or the amount of work that went into solving the puzzle, and it uses that then to decide which validator's block gets accepted. But yeah, there's only three. The other one is the avalanche one, which I'll come to in a second. I think I'm just really repeating myself here. Yeah, Ethereum moved over. They started off with proof of work, then they moved to proof of stake. So they had a different way of choosing a block producer. And then their consensus mechanism moved away from a variant of Nakamoto consensus to really having two things combined. So I won't go into what these are because it's not really important to us, but they've got two mechanisms. And the reason they chose two was that they're addressing two concerns. And these concerns also affect Solana. So those concerns are finality, the idea that we want to know that a transaction is final and is definitely part of the blockchain, and liveness. We want to make sure that our blockchain is going to proceed no matter what. And so within Ethereum, they've got two mechanisms, one's kind of addressing each. And so together they make sure that the chain has liveness and quick finality. Solana uses a variant of BFT. So as I say, there are various ways of implementing this type of mechanism. The fundamental part of the mechanism is that the system, the validators within the system, will vote upon the block that is produced. So they make a proposal about the block. Then the validators can vote upon this. And if you get enough votes, or if the block gets enough votes, then it will be accepted. So this is a reasonably straightforward mechanism, I guess, reasonably well understood. And you can work out the tolerance within the system, how much misinformation can exist in the system, but the system can still proceed. Now, one advantage of it is that once a block has got a majority of votes, then that is final. It can't then change. So we get quick finality from this. The problem, though, or one of the problems with this approach is that it could be that you don't ever get agreement about the block. The voting could go in such a way that we end up just never coming to agreement. So that's a potential problem with systems that follow this voting approach, the BFT approach. The problem is that there could be no liveness within the system. So the system could just kind of hang because we can't really proceed. We can't move on. I mentioned Nakamoto consensus already. I'll just finish talking about the avalanche consensus, which is quite interesting. It's a different way of approaching consensus, and it's illustrated here by these are meant to represent these pentagons represent different validators, and the color represents the state that they think exists within the system. So we've got choices here of gray or blue or yellow. And what we're looking at here is how a particular validator evolves over time. So this one starts off as yellow, and what it does is that it samples some other validators, and this is kind of done at random, etc. But what it will do is it will look at other validators and look at their state and then change its own state to match the majority of states that it sees. So if you imagine that this one then was sampling and it was looking at ones where there are more blue pentagons than gray, then or yellow, then it would change its own state to blue. And they just keep doing this. All the nodes are, or all the validators are continually doing this. But what that means is that we eventually converge upon one particular color for the whole network. All right, moving on to lesson 2. So we'll just quickly talk a little bit more about some of the components. So I've spoken about proof of history, but I didn't tell you how that worked or what it was. I ought to say actually that there are some changes coming up, and I've got some notes in a second about those changes. So this idea, this mechanism, is was designed originally for the first version of Solana, but there are some changes coming up as I'll tell you about in the way it works. But anyway, proof of history. It allows the nodes within the system to run their own clock, obviously without there being a central clock, because we don't have a central authority. We're a decentralized system. There's a link there to the documentation as well, so please do have a look at that. But the basic way we can do this is by using hash functions. So what's special about hash functions? What is it about them that allows us to do this? Well, they are deterministic. So, excuse me, if we run a hash function on the same input, we will always get the same output. But also they're one-way functions. So given a particular output, you cannot work out what that input should be. And there's collision resistance, which means if the input changes in any way, we will always get a different output. So how does this help us? Well, to help us with proof of history, or to help us get this kind of clock, what we do is we have an agreed upon starting point as the input, and then we continually take a hash of that and produce an output, and then take a hash of that and produce the next output. So we're continually hashing. We also have a count in there so that we can identify which one we are on at a particular time. Sorry. What this means is that if I gave you these the outputs from this, you will be able to put them into order. So you can order things given this, and this can only work in a certain order because of the way that hash functions work. It also allows us to get an idea of when something happened. It gives us an upper bound, sorry, and a lower bound on time. This is a little bit tricky to get your head around, so I'll perhaps just go over it quickly, but please do have a look at the documentation. Also, there's a good analogy with a water clock that may help you get to grips with it. But what we can do as we are going through and doing this hashing, we can add an input to excuse me, to this hash function, which was then going to change things after that. And so that then gives us an upper bound on the time that something happened. We can also get a lower bound by having something that has previously happened. We can then sign that and then input that into the system, and that gives us a lower bound on the time that something could happen. And with all of this, the cryptographic guarantees are given because, well, we have the hash function, so we know that can only work in a certain direction, and also that it's deterministic, that we know that it will always produce a particular output at any stage, and then we also have the signing that prevents malicious behavior as well. So all of this allows us to put events into this, or to use this proof of history and this count and the hash that is produced to reference things and to know that correlates to a certain time that something happened within the system. And the point is that we don't have this running centrally. All of the nodes within the system will be running this, and so they will all have the same sequence. So from the point of view of all of the nodes, we've got a sequence of events. Everything that happens within Solana can fit into these this count that we have, and we know where these things will fit. So it gives us a timing for everything. Now, the producing this and producing these hash values, that has to be done in sequence. We can't do that in parallel because each hash depends upon details from the previous one. So that has to be done in sequence. However, we can verify these things in parallel. So this means it is quite efficient. So if, for example, we have, as you've got here, we've got between 1 and 400 of these events that we've hashed. If we want to check these, we can start at 1 and move forward and check those, but we could also start part way through. And by running the hash function at, say, 0.300, taking that as the input and then taking the hash of that should give us 301, and we can check that that is the case. So this means that once we have the values, the checking them is quite quick, and we can do that in parallel. So that, yeah, that gives us an advantage as well. That gives us a performance advantage. And as I say, a useful analogy to help you understand that is with a water clock. Thank you for your attention today, everyone. I hope you found that interesting. We'll continue tomorrow, finishing off the idea about consensus, and then moving on, looking at Rust, and getting some more practical examples for you. See you then. Bye-bye.